Question 1 on test 2. Define a rational number in two different ways. Well, I would start with saying a rational, you can just put RAT, a rational number is a real number that, and then 1 can be expressed as a fraction, A over B, where A and B are integers and B, the denominator, is not 0. Or a second alternate definition is a real number that has a repeating you could also put in or terminating, a repeating or terminating decimal. We can just leave it at that. You don't have to put in the word terminating because really a terminating decimal like 1.3 is 1.3000 ... so it is a repeating decimal. It repeats zeros. But the word repeating is important. And so since these are two alternate definitions, we should be able to take a repeating decimal, express it as a quotient, and take a fraction and express that as a repeating decimal. Now, I don't think we expressed a fraction as a repeating decimal on this, but you know what you do. You divide the denominator into the numerator and find the decimal representation. So here, part B, express the rational number 1.151515 ... as a quotient of two integers, as a fraction. Well, I'm going to give it a name. Let's call n equal to 1.151515 repeating. Remember those ... dots. And now I'm going to, just to draw attention to this, I'm going to circle the repeating part. 151515. Okay, so I know that to move the decimal to the end of that repeating part, I would multiply by 100. So I'm going to change colors here just to stress to you, I'm not using this n up here except for just looking at it. Want to make my plan. 100n then is equal to 115.1515 repeating ... The decimal point is already at the beginning of the first repeating block, so I don't need to multiply n by any power of 10 before subtracting it. I will just subtract 1n, and that is 1.1515 repeating. Notice how I lined up my decimal point. So I will subtract, and I get 99n is equal to, all of the repeating decimal part of the numbers drops away, and we just have 114. So our answer is, this number n is equal to 114 over 99. You don't need to reduce the fraction, it just said express it as a fraction. So it doesn't need to be in reduced form. Question 2a. Define an irrational number in terms of its decimal representation. Well, I'll answer that first, but you should also know the other definition of an irrational number because we use it in our proofs by contradiction. So let's do both definitions here. In answer to the question, it just said in terms of its decimal representation, we would say, I'm going to call this 1 because there's really two definitions. An irrational number an irrational number has a non-repeating decimal. I'll just put DEC. A non-repeating decimal. That's an irrational number. Now, non-repeating decimals, let's give the second definition. They cannot be expressed as fractions. You can't use that technique we just used to find some multiple of the number to subtract one from another and wipe out the repeating the decimal part, because it never repeats. So the other definition is an irrational number is a real number that cannot be expressed as a fraction. And I mean a fraction of integers. It cannot be written as a over b, where a and b are integers and b is not 0. That's really important. It's not the answer to this particular question, but it's the second definition of an irrational number, and we use it in our proof by contradiction. When we prove that the square root of 2 is irrational, we said, suppose not. Well, then it would be rational, in which case we could write it as a over b, and we'll come up with a contradiction. Actually, in that proof, you're really using the fact that a rational number can be expressed as a quotient of 2 integers. So I'm not so sure this second definition is so applicable to that. It's mainly that a rational number can be written as a fraction. But anyway, you should know both definitions. B, find an irrational number between 0.2456 and 0.2456001. Well, I'm going to write the larger one on top, 0.2456001, and then leaving a space underneath between. I'm going to write the smaller number underneath it, leaving a space between the two. And I'm really careful to line up the decimal points here and the digits, the place value. 2, 4, 5, 6. Now the number above, the larger number, had 3 more digits. So I'm going to put 3 zeros on, just so that I have my digits lined up in the correct place value. So now I want to put a number in between. Well, I'm just going to, I know that this number will be 0.24560 because our numbers agree up to that point. Now, the next digit, if I make it a 1, that means that it is the same number, or eventually will be bigger than the one on top. So I can't put 1. I have to put 0 here. So this is where my hand is being forced. I have to put a third 0. And now I could put any digit I want. I'll just put a 5. And that makes the number between the two. That makes that number a rational number between the two. But this question said, find an irrational number. So I need to just put on a non-repeating decimal tail. How about 0, 1, 0, 0, 1, 0, 0, 0, 1, dot, dot, dot. So we had to make the digits agree as far as possible, and then the choice was in making that third digit there a 0. Well, actually it's the 1, 2, 3, 4, 5, the 7th digit 0, and the 8th digit 5. So that's an irrational number between the two. Question 3 was, do a proof by contradiction to prove that the square root of 3 is irrational. We are not asking you on the final to do a proof where you have to contradict a major theorem like this one does, but you should know how to do a proof by contradiction, and maybe you'll be contradicting something much easier. So I think we should go through this anyway. So do a proof by contradiction. We want to prove that the square root of 3 is irrational. So we suppose the square root of 3 is rational. In other words, suppose not, well then the square root of 3 is rational. Well, a logical consequence of that, using our definition, a rational number can be written as a fraction. I could say then the square root of 3 is equal, if it's rational, it's equal to a quotient of two integers, equal to a over b, where a and b are integers, and we know that b is not 0. All right, so the main thing is square root of 3 is a fraction. Now you have to do a little bit of algebra to write this very same sentence in a nicer way. We'd rather not have radicals. We'd rather not have fractions. So to get rid of the fraction, I'll multiply both sides by b. Notice the white. I'm just multiplying both sides by b. And so I get the square root of 3 times b is equal to a, because the b's cancel on the right-hand side. We chose that so that we would not have a fraction in our expression. Well, I don't like radicals either, and you know that radical 3 squared is 3. So squaring both sides might be a good idea. You could have done this, you could have done that first. You could have squared both sides. I'll show you that too. Whoops, trying to get it. So I'm squaring it here, in which case I get the square root of 3 squared is 3, b squared is equal to a squared. Now notice you could have done it differently. Let me take a different color here. You could have gone from here and just squared both sides and gotten 3 is equal to a squared over b squared, and then multiplied both sides by b squared, and you notice you get the same thing. Whichever algebra you like, you think is the easiest. All right, well now we have something here. 3b squared is equal to a squared. So in other words, if the square root of 3 is rational, then it can be written as a over b, and 3b squared is equal to a squared. And now I'm going to argue this quickly because you're not going to have to write out this whole argument, but we see on the left-hand side that 3 is a factor of the left-hand side an odd number of times. Why? Because b squared is a perfect square, and 3 is in b squared an even number of times. Even if it's 0 times, it's an even number of times. Every prime factor of a perfect square is in there an even number of times. So when we multiply it by 3, we put one more factor of 3 in, and that raises it up to an odd number. A squared is a perfect square, so 3 is a factor of a squared an even number of times. This is impossible. This is impossible because a number, we're saying that 3b squared is the same number as a squared. So of course they have the same prime factorization, and there is only one way to prime factor a number. The fundamental theorem of arithmetic, we called it the FTC, or you could call it the unique prime factorization theorem. There is only one way to prime factor a number. Therefore, this is impossible because it contradicts unique prime factorization. Therefore, our supposition was incorrect and the square root of 3 must be irrational. We know every real number, that's just all the decimal numbers. So a decimal number is either repeating or non-repeating. And so real numbers are either rational or irrational. What does it mean for two sets, two collections, to have the same cardinality? All right, well, you should be able to write a sentence. Two sets have the same cardinality. Let's see, how could I say? I could say there is a one-to-one correspondence between the elements, the members, the numbers, the elements of the two sets. In other words, there's a way to pair them up. Five through 9 are true-false questions. Write T or F at the end of the question. Now on the final, there may be a couple true-false questions, but you're going to have to explain why you give the answer you do. Number 5, every set of natural numbers contains a smallest number. Well, the important word here is every set and smallest number. Well, the natural numbers themselves start with 1 and everything else is bigger, right? 1, 2, 3, ... So any subset, any set of natural numbers is definitely going to have a smallest because the set itself does. So I would just write this for n and write true. It is true. Every set of natural numbers contains the smallest number. Number 6, oh, but by the way, that's not true for a biggest number, is it? If we put the set of evens, for example, there's no biggest even number. But there is a smallest, 2. 6, if two sets have the same cardinality, then every correspondence between their elements is 1-to-1. This is absolutely false. And I want to keep reiterating the importance of a list in the case of infinite sets. So I'm going to make a list here. And, well, let's try to make a list of the integers. And let's say that we did as you did in the beginning when we've got our first suggestions. You said, well, what if I write -3, -2, -1, 0, 1, 2, 3. When you make that list, you definitely make a correspondence between the integers and the natural numbers. Any list creates a any list creates a one-to-one correspondence between the natural numbers and the numbers on the list. So certainly this is a correspondence between the integers and the natural numbers, but all the integers are not on the list. So although this is a correspondence, not all integers are on that list. So this is not one-to-one with the natural numbers. There are many ways to make correspondences that are not one-to-one. A simplest case, let's take the set containing 1, 2, and 3, and the set containing A, B, and C. You could pair 1 with A, 1 with B, 2 with C, and 3 with B. There's a correspondence, but it's not one-to-one because 1 is paired with A and 1 is paired with B. And you could say 1 is paired with B and 3 is paired with B. It's not 1-to-1, but it is a correspondence. When we say that two sets have the same cardinality, we mean that there exists a way to make a 1-to-1 correspondence between their elements, not that every single correspondence is 1-to-1. Number 7, the cardinality of the rational numbers is the same as the cardinality of the real numbers. This is false. This is false, and the reason why is that we know that the cardinality of the rats, the rationals, is equal to the cardinality of n. We found a way to list all of the rational numbers, and you found another way on your homework when you did the problem that was in the book using that grid. So we know that the cardinality of the rationals is equal to the cardinality of n, and using Cantor's diagonalization, we proved that that is not equal to the cardinality of the reals. So it is false. 8. The fundamental theorem of arithmetic tells us that there are several ways to prime factor natural numbers. Well, no. The fundamental theorem of arithmetic tells us, another word for it is unique factorization. There is a number is either prime itself, or a natural number is either prime itself or it is uniquely factored into a product of primes. So that was false. And number 9, the set of integers is I equals left curly brace dot 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 minus 3 minus 2 minus 1 0 1 2 3 dot 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 right curly brace. And the set of squares of all integers is capital S equals left curly brace 0, 1, 2, 4, 9, 16, 25, dot 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 right curly brace. It is clear that the integers has a larger cardinality than the set S. This is false, but you have to think of why. We have proven by listing the integers. We listed them. We made a list. We said it was 0, 1, minus 1, 2, minus 2, 3, minus 3, dot 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 is a list. What I gave you above is not written as a list. It's just using set notation. But this is a list of all integers. So the cardinality of the integers we know is equal to the cardinality of the natural numbers. Any infinite set that can be listed has the cardinality aleph naught, or the cardinality of the natural numbers. Well, S is given to you as a list. 1, 0, 1, 4, 9, 16, etc. So S is given as a list, and we could say clearly the cardinality of S then is equal to the cardinality of n. Therefore, they have the same cardinality. This implies that the cardinality of S is equal to the cardinality of I. They both have the same cardinality as the natural numbers. So it is not clear that I has a larger cardinality than S. Number 10, the set of natural numbers is n equals left curly brace 1, 2, 3, 4, dot 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 n curly brace. The set of natural numbers. A, give an example of a subset of n that has the same cardinality as n. Well, that's unusual, isn't it? Because our experience is with finite sets, and we always know that subsets have a smaller cardinality than the parent set. But in infinite sets, that's not the case. For example, the evens. I'll just write capital E. The odds, I'll write capital O. The primes, I'll write capital P. The Fibonacci's, I'll write F sub n. The Lucas numbers, L sub n. These are all examples. The multiples of 10, I'll write that with set notation. 10, 20, 30, 40, ... These are all infinite subsets of the natural numbers, which have exactly the same cardinality as the natural numbers. This does not happen in finite sets. Part B, give an example of a subset of n that has a different cardinality. Well, that's easy. How about the set containing 1, 2, and 3? That's a subset of the natural numbers. It is a finite subset. So really, any finite subset would have been a correct answer. But an infinite subset would not. Any finite subset of n has a smaller cardinality than n. Problem 11. Explain the fundamental difference between finite and infinite sets in regard to their cardinalities and the cardinalities of their proper subsets. Many of you did not read the question carefully enough. Read every word. Repeat it to yourself in your head. What is the difference in regard to their cardinalities and the cardinalities of their proper subsets? Well, one way we could say this is that, well, proper just means proper subsets. Proper means that it's not equal to the whole thing. So I'll just use the word subsets, meaning subsets that don't include the whole set. Subsets of finite sets have a smaller, or I should not have smaller cardinalities than the, I'm not sure how to say this, the big set? Okay, I could use the word big set, or I could use the word parent set, the set they were taken from. For example, if I take the set of numbers 1, 2, up to 100, and I take a subset, the set containing 1, 2, and 3, that is a subset, but the subset has cardinality 3, and the larger set, the big set, has cardinality 100. Infinite sets however, have or let's say, well, have subsets with the same cardinality. Now I refer you back to the last problem as an example. Not all of their subsets have the same cardinality, but infinite sets do have subsets with the same cardinality as the big set or the parent set. Question 12 has to do with the list that we made on a video and did it in class. A list of all rational numbers, each on the list only once. If we can do that with any infinite set, if we can make a list where each element of the set is on it and only one time, we have created just by the list a one-to-one correspondence with the natural numbers. So this below is a set of rational numbers we did in class using 4 stages. We were convinced that our method would include all the rational numbers, each only once. And then I give you like the first, I don't know, 30 or 40 numbers on that list. A, which rational number corresponds to the natural number 12? Well, the natural number 12, its pairing will be sitting in the 12th position. So I just go over 12 numbers, and I find that 3 halves, if you count over to the 12th position, the 12th number on the list, we know that the rational number 3 halves corresponds to, you don't have to write these double arrows, corresponds to the natural number 12 because it is 12th on the list. What natural number would correspond to the rational number minus 0.75? Well, first we have to write it as a fraction so we can see where it is on the list. 0.75 is 3/4, so this is minus 3/4. That's the fraction in reduced form. So we go find it. Here's minus 3/4, and you just count over, and you will find that minus 3/4 is the 19th fraction on the list. So it corresponds to the natural number 19. Part C, still referring to our list. What is it about our method that guarantees no duplications on the list? That is, what did we do to avoid listing a number twice? And the best answer here would be we listed only the reduced form of a fraction or of a rational number. So in other words, we didn't put 2/4 on the list because we already had 1/2. And the way that we created the list, we came upon the reduced form before we arrived at numbers that were the same number but not in reduced form. In other words, we came to 1/2 and put it on the list in the 4th position before we got to 2/4 or minus 2 over minus 4 or 100 over 200. So it was already there. D, if I had made a mistake and I put 12/24 on the list in the 100th position, why would the correspondence then not be 1-to-1? Well, if you look up at the list here, you see that 1/2 is on the list in the 4th position. So the number 1/2, or let me call it something else. Let's say the number 0.5, put it in its decimal form, would correspond to 4 when it was put on as 1/2. It would also correspond to 100 when it was put on the 100th position as 12/24. So the correspondence would not be 1-to-1 because the number 0.5 would be listed twice and therefore correspond to 2 different natural numbers. Part E, again referring to the list. Describe the 1-to-1 correspondence set up by the list. What does a natural number n correspond to in the listed set? There are 2 ways you could answer this. You could say n in a sentence. You could say n corresponds to its, the natural number n, to the nth number on the list. In parentheses, I'll write every number on the list corresponds to its position on the list. Now, the easiest way to say this is that n in the natural numbers corresponds to nth number on list. I've just drawn like a double arrow, and you just avoid writing a sentence. You just give it in this correspondence notation. N, double arrow, nth number on list. Part F, exactly what does the existence of this list prove about the cardinality of the rational numbers? Everybody better get this one right if it's on the final. We went to all that effort to show that since the rationals could be listed, the cardinality of the rational numbers is equal to the cardinality of the natural numbers. They have the same cardinality. They are the same order of infinity. Number 13, let capital S be the set of all real numbers having only digits 2 and 3. Give an example of a rational and an irrational number in S. Okay, well, these numbers are scattered all over the real number line. You have big ones. You have numbers like 3333333.22222. It's really big. And you have negative numbers, positive numbers, but they only have digits 2 and 3. So there's so many answers you could give here. A rational number, well, why don't we just say 2.222 repeating? That has only digits 2 and 3. It doesn't have any 3's, but 2 and or 3. Another example of a rational, we could say 2.323232. ... An irrational number, well, how about 2.323323332 ... meaning it is a non-repeating decimal that only has digits 2 and 3. Part B, suppose you are given an infinite list of numbers in S. Write a rule that will choose the digits of a number M in S that is not on the list. Okay, well, I have to make it in S, so I can only use digits 2 and 3. So here's my rule. Make the nth digit of M a 2 if the nth digit of the nth number on the list is 3. If the, I'm going to great detail here, if the nth digit of the nth number on the list is 2, then make the nth digit of M a 3. And that'll do it. Now, I know that's a lot of words, but heck, this is one question on the test. You can take the time to write 2 sentences. Be careful. If you don't write a correct rule, you're not going to get complete credit for it. I want to say, too, this was an example where we were not looking at all of the real numbers. Cantor's method that we learned in the video had us just pick 2 digits that we wanted to use and create a number not on a list of real numbers, all of the real numbers, and thereby we showed that real numbers could not be listed. So be sure and look over the example in that video. Go back and look at the video and look at the Cantor's method that I taught you in the video, because that set was R was the real numbers. This S is a subset of the real numbers. It's exactly the same concept, just see why. How do you know for sure that your rule will not produce the 1,000th number on the list? Well, it will be different in at least its 1,000th digit. What does this mean about the cardinality of S? All you have to say is that it's greater than the cardinality of the natural numbers. But all right, since S cannot be listed, there is no one-to-one correspondence with capital N. Therefore, the cardinality of S is greater than the cardinality of N. Part E, apply your rule to this list started below. That is, write the first few digits of a missing number, capital M, in S that is not on the list. Okay, well this one I know everybody can do. And you go start your diagonal with the first digit after the decimal point. So this is, I'm just going to circle them as I go down here. I'm circling the numbers on the diagonal, starting with the digits after the decimal point. So we said we're going to make a missing number M, and I can make it 2-point or 3-point. We didn't say what we were going to do with the digits to the left of the decimal point, but the trick is in choosing those to the right. I just go down this diagonal. I see a 3, so I make my first digit a 2. The second digit of the second number on the list is 2, so I make my second digit a 3. The third digit of the third number on the list is 3, so I make my third digit a 2, and so on. I get the number 2.2323232 ... Got to put that in, means and so on. That number will not be on the list. Part F was extra credit on exam 2, but hopefully you can think about this now and understand what could you say about the cardinality of S if S were to contain only the rational numbers with digits 2 and 3. Well, if S were a subset of the rational numbers, let me write that. If S, this means subset, sideways U. If S were a subset of the rats, and we know that the rationals have cardinality out of naught, in other words, cardinality of the natural numbers, S is an infinite subset of a set that has the same cardinality of N, well then we could conclude in that case, if we threw out all the irrational numbers in S, then the cardinality of the set would be equal to the cardinality of the natural numbers.